The last talk of today is by Shen. He's going to tell us about special Lagrangian fibrations in low Calabi surfaces and mirror symmetry.
So first, I want to thank the organizers for the invitation to this wonderful conference. I also want to apologize that due to the time zone, I'm actually in West Coast, so it's hard to attend every talk. So today I want to talk about special Lagrangian fibration, low Calabi surfaces, and mirror symmetry, and more about its applications outside of mirror symmetry, actually. So, the outline of talk, well, sorry? So the first, I will introduce the SYZ conjecture in the geometric setting, and I'll explain the main theorems and the sketch of a proof. And I'll explain what I mean by SYZ mirror symmetry for low Calabi surfaces, and then I'll explain the applications. So I will first explain the setup. So we have Calabi manifolds. You probably see it in a lot of places. For Calabi, I mean a complex manifold with nowhere vanishing holomorphic top form. And more than that, I will actually ask for a Kähler form, which is satisfy the complex modular equation. And here this C is some constant. So there are some examples. So if you take a degree phi hypersurface in P4, by adjunction formula, you know that there exists such a nowhere vanishing holomorphic top form. And so usually this is what people call the quintic threefolds. The hard part is to produce the Kähler form that satisfies the complex modular equation. And this is the Yao solutions to the Calabi conjecture. And in this case, this kind of C really doesn't matter. For the non-compact situation, it's more complicated. So the examples are first given by Tian Yao. So they consider as a Fano manifold, and they throw away a smooth anti-Kähler divisor. And so then the complement is again easy to see there exists in nowhere vanishing holomorphic top form. But then the hard part is to solve the complex modular equation, and it's done by Tian Yao. And so now here that the C does matter, and this you can have a whole range of this number C here. Right. So this is my definition of Calabi that will be used in this talk. So one reason we care about Calabi manifolds are there because of mirror symmetry, and it's a duality between simplex geometry of one Calabi with complex geometry of its mirror partner. And so, for example, we have homological mirror symmetry that's tell you that one Foucault category of one Calabi is isomorphic, is equivalent to the Dirac category or sheaf on its mirror. So mirror symmetry gives you some interesting predictions in numerical geometry. For example, Candelas de Losa, Green Presser, they proved that they predict the number of rational curves of degree D in a generic quintic via the principle of mirror symmetry. And mirror symmetry can also extend to Fano. I think it's due to Kontsevich. So So the mirror of Fano manifold, it's a Landau-Ginzburg model. It's a holomorphic function from some complex manifold to C. And this holomorphic function should reflect the geometry of Y. So for example, it can reflect the simplex geometry of Y via this Foucault category Y that's isomorphic to factorization of the superpotential, or it also reflects the complex geometry of Y. So for example, you look at a Foucault side of category of superpotential that recover the Dirac category of covariant sheaf on Y. And so then the question is, can we find this superpotential? And so one solution by Cho and O is that if when Y is Torifano, then W is the weighted count of holomorphic disks with boundary on the MMF fibers. And so technically, I probably should mention that we're actually only counting Maslov index 2 disks. And so run an example is that when Y is P2 and W is just X plus Y plus 1 over XY, which is a holomorphic function from C star squared to C. And it's not too hard to see that there are 3 critical values of W. Okay. So there's some story. And so I need to tell you what are spatial Lagrangians to explain the spatial SYZ conjecture. So this notion is introduced by Harvey and Lawson. So they said a half-dimensional submanifold of L and the Calabi X. If the Kähler form reached on L equal to 0, then we say it's a Lagrangian. And furthermore, we can find a constant theta such that the imaginary part of the holomorphic top form retreat on L is strictly 0, or you can twist it by this minus exponential minus I theta. Then we say that this Lagrangian is special. We call it a spatial Lagrangian. And spatial, so these 2 equations coupled together become some higher order nonlinear PDE. And so it's really very hard to solve. But one payoff is that they give you area minimizers. And so there are quite some interest in geometry that we want to know more about spatial Lagrangians. And so the conjecture of Strominger, Yau, and Zaslow says that Calabi manifolds, they would admit spatial Lagrangian torus fibration near large complex structure limits. It's like, which is some terminology from physics, but we can view it as some kind of degeneration. And more than that, if we're interested in mirror symmetry, then we might want to ask, how do we produce the mirror? And here is a recipe from SYZ that the mirror Calabi can be constructed by you first construct a spatial Lagrangian torus fibration, and then you take the dual torus fibration, and that will produce the mirror. And so there's a modified conjecture of concept Soberman that near this large complex structure limit, you might not really see the spatial Lagrangian, but you expect that the whole Calabi manifold collapse to some affine manifold with singularities. And so, or if you see spatial Lagrangian fibrations, then the torus fibers are collapsing at a large complex structure limit. Or the other way, I will view this as like when you have a sequence of Calabi and you see the SYZ fiber collapsing, I will view that as the definition of the large complex structure limit. Okay, so any questions? Okay. So why do we care about SYZ conjectures? So it's important in various aspects. It gives some geometric description of Calabi manifolds and produce a recipe to construct a mirror. And so from the series of work, Leon, Yao, Zaslow, and Fan, Liu, Truman, Zaslow, and Chen, Pomigliano, Ueda, and there's probably a never-end list. And the SYZ conjecture give a guidance how branes mirror to each other in a homological mirror symmetry. It also motivates the family flow mirror proposed by Fukaya, and also realized by Tu and Abze and recent work of Han. And you probably will hear more in Han's talk later this week. And also in terms of algebraic geometry, there's another approach by Concept Sobelman, and later the program of Gross-Zieber, Gross-Hagenkiel-Zieber. in a more algebraic geometric point of view. Okay. So if I'm saying that SYZ conjecture is wonderful, so I probably need to give you some examples. So the two examples that I know is you start with an elliptic curve, and you can write down the flat metric, and there's an obvious volume form. And then there's an obvious fibration by you just take the horizontal slice of the fibration. So this is a torus, and then you just take the horizontal slice, and so this gives you an obvious fibration. So this is the first example. It's easy to generalize to a higher dimensional tori, but it's flat metric, and so everyone knows how to deal with it. There's another example sort of given by Harvey and Lawson when they introduced Calabi submanifolds. So if you start with the Calabi surface with an elliptic fibration, and then one can do something called a hypercube rotation, since that introduced in Uma's lectures earlier, and then X will admit a special Lagrangian fibration. And so this hypercube rotation procedure, they will make the holomorphic curve and the original Calabi surface into special Lagrangians in a new Calabi surface with a new Ricci flat metric and holomorphic volume form. So these are the two examples that I know. So to understand the SYZ conjecture, say the original version better, there's a sequence of work. Oops. Okay, so McGraw that he constructed topological torus fibrations on quantic three folds, and later he introduced has the construction of nowadays called gross fibrations, which with respect to not to the true Ricci flat metric, but to some other kilometric, but in the setting with torus symmetry. And so these examples are usually non-compact, but these are very handful and important examples in simplex geometry nowadays. And so when people are excited about SYZ mirror symmetry, originally people expect that the discriminant locus of the SYZ fibrations are codomain true, but then Joyce gives some examples codomain one singular fibers in an SYZ fibration, and which apparently make the analysis much more harder. And Castano, Barnard, Matsey, they enhanced the construction by Gross to Lagrangian fibers on quantic three folds. And so I think there's probably more work I should mention, but and there's quite a while in the middle, there's not much progress on the original conjecture until very recently. There's a work of Yan Li. He constructed, say, on Fermat hypersurface on a large region, there exists SYZ. Exists a special Lagrangian tori. And the work that I'm going to say talked about today. All right, so I will need to tell you what geometry we're talking about this SYZ fibration. So, so the first player of the game is the Pazzo surface, a complex surface we call it the Pazzo, if its anti-column divisor is MPO. And so by classification of surfaces, so Y is either P1 times P1 or a bro of P2 at generic D points. So in particular, you will see that there's 9 families here. Here, you can bro up from 0 to 8 points. You have 9 family and P1 times P1. So in total, there are 10 families of de Pazzo surfaces. And we call the degree of the de Pazzo surface to be the self-intersection of the anti-column divisor. And it's not hard to show that every de Pazzo surface emits a smooth anti-column divisor. And so the other player of the game is called the rationally surface. So a rational surface is a rational surface with a minimal elliptic fibration. So its name is pretty manifest. And any rational surface can be realized as grow up of 9 points on P2. And so you start with, say, a pencil of cubics, say, and then 2 cubics will intersect at 9 points, counting with multiplicity, and you grow up those 9 points that will give you a rational surface. And so since it's a grow up P2 at 9 points, so you can iteratively compute the canonical bundle. And so its canonical bundle or anti-canonical bundle is given by the sheaf that's given by the fiber. And so the possible singular fibers inside rational surface are classified by Pearson. We're particular interest in a kind of fiber that's we call an ID fiber. And so it's like a wheel of rational curves. And since it's an anti-canonical divisor, and so a rationally surface with an IK fiber or ID fiber is a Lagrangian up here. That's sort of finally you see the keywords of the workshop. And so it's this one fact that there are 10 deformation families of pairs. And so you will see one for each D, except D equal to 8, you get 2 families. So in total, again, you get 10 families. You see the magic number.
So you should have enough multiple fibers?
Yeah, so I will, so my, in the definition of my elliptic fibration, I will require a section, and that will rule out the situation of multi-fiber. Yeah. Thanks for the question.
What's the answer? So it's, the answer is no, you don't allow.
Sorry?
What's the answer to the question?
So I think the question is where there will be like a multi-fiber, I guess, if I understand right. But my definition of elliptic fibration, so I will require a existence of a section, which says that one cannot have the fibration cannot have like multi-fibers.
Okay.
Yep. Any other questions? And so, oops. So the vector surface and rational surface, they're both Calabi pairs. They will give you really like Calabi in my definition. And so it's not too hard to see that if you look at the complement of a smooth anti-canonical divisor, there exists a holomorphic 2-0 form, which is actually meromorphic on the total space of Y, but it has a simple pole along D. And the result of Tianyao that I mentioned earlier, there exists Ricci flat metric on W. Actually, there are tons of Ricci flat metric on this complement, such that it satisfies the complex Mongeon-Pei equation and asymptotic to some model geometry that I'm going to explain later. Similarly, if you take, I'll always use this Y check as the notation for a rational surface and D check for an ID fiber. And so if you remove any fiber, then the complement, because it's a fiber is an anti-canonical divisor, and so the complement again admits a holomorphic 2-0 form, which is actually meromorphic, was on Y check and has a simple pole along D check. And the work of Heil, that he proved that there exists Ricci flat metric on the complement and satisfy the complex Mongeon-Pei equation. At infinity, it's asymptotic to some other metric that I'm going to explain later. So these two gadgets are both Calabi in the sense that I start with. And so, and moreover, that because of the dimension reason, they're both hyperkähler. And so you can talk about a hyperkähler rotation on this basis. Oops. Mirror symmetry between the bezel surface and rational surfaces is widely studied. It's first probably by Orukazakov, Olov. They prove homological mirror symmetry, such that the bezel surface is the right category current sheaf is isomorphic, is equivalent to the Fukaya-Saito category of superpotential. And the algebraic potential of so one important observation is that the algebraic potential of the bezel surface can be compactified to rational surface topologically. But worth to notice that because of the definition of Fukaya-Saito category, the complex structure of W really doesn't matter. There's a earlier work of Carter, Pompola, Siebert. They construct a mirror family for the bezel surface was a smooth and divisor, and then later Gross, Hack, and Q have this construction of when D is maximally degenerate, or this YD is become a degenerate to a Lagrangian pair. Saito has his way of understanding this mirror symmetry via the Lipschitz fibration, and Lund, Pierzjakowski proved the mirror symmetry for in the level of Hodge, like exchanging the Hodge numbers, but here the Hodge numbers need to be suitably interpreted. And Doran Thompson has a suggestion on the lattice theoretical mirror symmetry similar to the work of Dogachev. Probably there's a huge list I won't be able to exhaust. And so probably very different from most of other talks, I will give you some motivations from the fields and from differential geometry, why we're going to expect such results. So when Hai construct this matrix, he observed that these two geometries that I mentioned earlier, this the bezel surface, you throw a smooth angle divisor, and the rational surface, you throw an ID fiber. They have the same asymptotics in the sense that if we compute the curvature decay, the injectivity radius, volume growth, etc., all the sort of Riemannian geometric invariants, they're exactly the same. So because hypercare rotation does not change the underlying space, so it's natural to ask, are the two geometry related by hypercare rotation? And if the answer is yes, then when we do hypercare rotation, we get this complex manifold. Can we identify the metric? In other words, if I start with the Tianyao space, I do a hypercare rotation, do I get the metric that constructed by Hai? And so these are some very natural questions from the differential geometric point of view. And from mirror symmetry, we're probably can ask the following question: can we read of, say, the Lambda-Ginsburg potential just from the SYZ fibration? So recall that the SYZ fibration is only defined inside the interior, while the algebraic potential really depends on the compactification. And so if this is the case, that means that the metric perspective probably captures certain information of some particular, some favored compactification, which is highly non-trivial. So now I will be able to explain the main theorem and the sketch-up proof. And so this is a joint work with Collins and Jacob. So if you start with the the bezel surface or rational surface and a smooth entangled divisor, then the complement, you can find a special Lagrangian fibrations with a special Lagrangian section with respect to the Tianyao metric that I introduced earlier. And so this gives you, this confirms some conjecture, earlier conjecture of Yao and Oru. So in the case of P2, you will get a special Lagrangian fibrations on P2 on the complement of smoothly the curve with 3 nodal singular fibers. And for a generic rational surface, you will get a fibration with 12 singular fibers. And this number is not too hard to guess from the autocharacteristic, but the hard part is to really produce a special Lagrangian fibrations itself. And for people who are interested in mirror symmetry, so the number 3 here might already touch your nerve because the superpotential for P2 has 3 critical values, which coincide with this number 3. And so maybe that give you some hint. There's something interesting going on. More than that, we proved that if you do a hypercube rotation of this complement of smoothly the curve inside the pencil surface, particularly in this way, then the hypercube rotation can be compactified to a rational surface by adding an ID fiber at infinity, where this D is determined by the degree of the pencil surface. And later that Heinz-Sanville-Gauss zone has a complete different proof later. And so recall that earlier that we mentioned that there are 10 deformation families of the pencil surface and 10 deformation families of rational surface with ID fiber. And so this correspondence respects the deformation family. In particular, there are 2 families of the pencil surface of degree 8, and there are 2 families of rational surface with IA fibers, and they match in an X or the favored way. And in particular, actually, we see that the SYZ fibration has a spatial Lagrangian section this way, which is non-trivial because that usually it's hard to get a non-compact spatial Lagrangians. And also tells you that the base of SYZ fiber is actually R2, because otherwise that you will get some harmonic function, which is non-constant on a Ricci flat manifold, which contradicts to a theorem VL. So I also want to mention particularly that when Y is P2, then the hypercube rotation gives you the mirror. And so recall that the mirror, so the mirror of potential of P2 is given by X plus Y plus 1 over XY. And so it has 3 singular critical values. And for generic fiber, you will find out it's an elliptic curve with 3 punctures. And so the hypercube rotation actually give you just filling all the 3 points, 3 holes on the generic fibers. And so that give you a space which is X-checked. And so in this example, that the hypercube rotation exactly gives you the mirror. So this is probably like a very sort of counterintuitive after the work of Gauss-Wilson. Right. So there's another thing that this workshop is about Lagrangian pairs, or Lagrangian interiors. So if we consider the case of rational surface with an ID fiber, and then you look at, so now this is really the Lagrangian interior, then it also emits a spatial Lagrangian fibration with respect to the Heinz metric, or in some sense, like a more generalization of that I will mention later. And moreover, a suitable hypercube rotation, you can be compactified to another rational surface by adding an ID fiber. And so now you get these 2 spatial Lagrangian fibrations, one on the pencil surface, you throw away the smoothly curve, and the other one is like a rational surface relative to an ID fiber. And so as things that people are expecting, these 2 Calabi are mirror to each other. It's natural to expect that these fibrations are dual to each other. So, okay, so now I need to tell you a little bit more about the model geometry. So on one hand, near inside the Calabi near a smooth entangled divisor. And so the neighborhood is modeled by its normal bundle. And so on this normal bundle, the fiber coordinate is called W, and you can like pull back the holomorphic volume form D to the total space of the bundle, and then we call it omega D, and then you wage it with D omega. Sorry? So that gives you the holomorphic 201. On the other hand, you're going to choose, because that this line bundle is, if it's true, you take a formation metric such as a trim form, it gives you the receive flat metric on D. And then for every point, you view this as a point of section, and then you take the norm of it and take minus log to certain interesting power 3/2, and then that gives you the potential for a receive flat metric. And so this is what I call the Calabi n sets. It gives you a model geometry at infinity. On the other hand, an IK fiber, if you have an elliptic fibration with over a disk with an IK fiber and over a region, you can, this model by Abel-Jacobi map, you can identify as a C times a disk, a quotient by some lattice. And this particular period will give you, tell you that the monodromy is 1K01, or equivalently that the central fiber is of IK type. So if I call the fiber coordinate X and the base coordinate U, then du over U, which dx is as a holomorphic 201, which is obviously nowhere vanishing. And one can write down some expression that's written down by Green, Shapir, Vafa, and Yao. And this is called a semi-flat metric, which is flat along each fiber, but globally it's not really flat, but receive flat. And so these are the model geometry infinity for rational surfaces. All right. So the second ingredient is the Lagrangian main curve flow. So that L be a graded Lagrangian submanifold. What I meant is that, recall that if you restrict the holomorphic tough one on L, the Lagrangian condition guarantee that it's always the volume of L is twisted by the EI theta. And so originally the theta is a function from L to S1. If you can lift it from L to R, then we call it as the Lagrangian is graded. And in particular, if this theta is simply a constant, it is exactly the definition of special Lagrangian, because you get the imaginary part of E minus I theta times omega reached on L is strictly 0. So in this case, the mean curvature is given by the connection and theta, and you twist it by the complex, almost complex structure. And so the mean curve flow is you're going to deform the Lagrangian in the direction of mean curvature. And so it's proved by Smozek that the Maslov zero condition and the Lagrangian condition will be preserved under the mean curve flow in the Kiel-Einstein manifolds, in particular Calabi manifolds. And so this is the reason why we call it the Lagrangian mean curve flow, because if you start with Lagrangian, then it will keep being a Lagrangian along the flow. So if we're in a lucky situation, we can prove the Lagrangian mean curve flows converge smoothly, then that means that when t goes to infinity, that you get 0 here. That means that the mean curve equal to 0. And by definition, the mean curvature equal to 0 will tell you that theta is a constant. And then it's a special Lagrangian. So this is one of the reasons when they construct Lagrangian mean curve flow is to expect to flow to some special Lagrangians. But you can see that that's for quite a while ago when Smozek introduced this. And so I'll give you a continuative proof. So the first thing is that, I forget to mention whether the special Lagrangian n says that at infinity. So now in this case, there's D. So recall that D has a lot of special Lagrangians because that you have a lot of straight lines inside the flat torus, and then they can like after quotient by lattice, that they're as spatial Lagrangian S1. So you look at those like for each point on D, you look at its preimage of the normal bundle and look at those like a constant length as like a norm epsilon points above it, and they give you an S1 bundle. Actually, the Lagrangian condition will tell you that this S1 bundle has trivial Chern class, and so it's a trivial bundle, and so that gives you a torus, and that will be the n sets for the spatial Lagrangian for Calabi n sets. For the other case that you look at the vanishing cycles, and you draw a circle downstairs, and you union the vanishing cycles along this curve, and that give you. It's not hard to show that it's a spatial Lagrangian with respect to the semi-flat metric. And so we start with this n sets spatial Lagrangian, and then we're going to run the Lagrangian mean curve flow. And then we're going to pray that Lagrangian mean curve flow converges smoothly. And so the difficulty is that all the existing tool in Lagrangian mean curve flow usually requires that the geometry is non-degenerate. And usually you need some sign on the Ricci curvature, but we're in a very bad situation where the geometry is very degenerate at infinity. And there's no sign on Ricci curvature. And this is a main difficulties we need to overcome. But the payoff is that our construction will construct many examples of spatial Lagrangians, not necessarily as torus, actually. And in higher dimension as well, we will be able to construct a lot of new examples of spatial Lagrangians. So then you do a hyperrotation of spatial Lagrangian torus to an elliptic curve. And then you can try to deform the curve as a map, as a J-holomorphic curve. And then you prove that its deformation will be open and closed, and that's the whole manifold you want to deal with. And so then that will help you to give you a fibration structure. And then you can try to compactify using this fibration structure. You can compactify it, and using the Emery-Cordara classification, you can conclude that the geometry that you compactify is actually a rational surface. And then you do a hypercube rotation back, you get a spatial Lagrangian fibrations. This is give you a continuative proof. Right, so with all of this, then I can explain the mirror symmetry for log Calabi surfaces. So we're actually in a weird situation. So usually when we in the differential geometric point of view, if you start with something that you expect it's Calabi, and usually the hard part is that we don't know if there exists a spatial Lagrangian Ricci flat metric. For example, if you give me a random Lagrangian pair, in general, we don't know if there exists Ricci flat metric or not, or actually, and it's a very hard problem. But for this particular setting, we actually have too many Ricci flat metrics. And so then it makes it hard to define what is the Kähler moduli. And so if we consider the long exact sequence of the pair, so recall that D check is a wheel of P1, so H1 is Z. And so the long exact sequence pair that will give you a cycle inside here. In H2 of the Lagrangian interior. And this is called the bad cycle. And you will see why it's called a bad cycle from the following theorem. So actually what Hein proved is that if you start with any Kähler form on X track, so recall the X track is you start with a reference surface, you throw an ID fiber. and the volume form is finite, and the Kähler class or the cohomology class is pairing 0 with C, then you can find a Ricci flat metric in the original de Rham class. Satisfy the complex modular pair equation, so it's Ricci flat, but also it requires that some constant here is large enough. And so it's a very different feature that in differential geometry, when in a non-compact situation, this alpha can change. And moreover, the Ricci flat metric he got is asymptotic to some semi-flat metric. And so now you can see why it's called the bad cycle by high, because that it seems that if the pairing is not 0, then you might not get Ricci flat metric. So this looks like an obstruction to it. And on the other hand, you will see that you start with any Kähler form, you run this machinery, you get a Ricci flat metric. And so, but they're all in the same de Rham class. And so we might not, we don't know if there exists sort of like a uniqueness in each Kähler class. So it's very different from the case of compact case. You have a theorem of Yau. And so to explain what is the Kähler moduli of this non-compact Calabi Yau, so with Tristan Collins and Adam Jacob, we proved the existence. So we have a similar theorem as above that what Hai proved, but we can remove this L2 condition. So that's a small improvement. But the more interesting part is we remove the bad cycle constraints. So what bad cycle constraint, like the definition of bad cycle a priori looks like an obstruction to exist in Ricci flat metric, but actually it's not. And so in particular, you found a lot of new Ricci flat metrics. And moreover, we proved some kind of uniqueness. So if you have two Ricci flat metrics with the same volume form in the same de Rham cohomology class, and asymptotic to some semi-flat metric, a priori they might asymptotic to different semi-flat metric. As long as these two, they decay to each other, and such the difference has a polynomial decay, which is rather weak condition, then you can say that these two Ricci flat metric are the same. And so the reason why this is hard is because this complement X check here is not Stein. And so you don't have the DD bar lemma. And so a priori that this 2 omega here you start with, they might not be differed by a DD bar or something. Or in other words, they might not fall in the same Bachan cohomology class. And so it's not cleared a priori where we start to solve the complex modular pi equation. And so
I have a question. May I ask the question?
Yep.
So this semi-flat metric, approximate asymptotically semi-flat metric condition, is that intrinsic, or what structure do you need to define this notion?
If you have, so usually if you have some asymptotic infinity, you can try to solve the complex modular pi equation. But then usually, yeah.
But what is the semi-flat metric then?
Oh, so this is the metric written down here. So
In this particular case, you have something, but let's say I've just some kind of Kähler manifold with some, and I mean, how do you define, without knowing something about your space, how do you define a semi-flat metric?
No, in general, there's none, right? So this sort of semi-flat or semi-Ricci flat metric only happens when you have a fibration structure.
Okay.
And fibers are Calabi, I would say, for example.
Okay, thanks.
Yep. You're welcome. Thanks for the question. So with this kind of uniqueness theorem, so now you can define the Kähler, sort of the Kähler moduli. So we consider all the Ricci flat metrics asymptotic to some semi-flat metrics. And then we modular the translation. So because that you can, for Lagrangian surface, there are some holomorphic sections. And so you can translate section, you can use translation to give you a biholomorphism to pull back the metric. And so we modulate this equivalence. And the non-trivial part is that after you quotient out this non-trivial equivalence, then you get finite dimensional space. And then you get something that you can identify with the Duran cohomology class, and you get an empty cone, a non-empty interior, a cone with non-trivial interior of dimension 11 minus d, which is probably one more, is sort of higher than the expected dimension. If you want to talk about mirror symmetry, you have to cut out by the cycle you're going to choose for the spatial Lagrangian fibrations, and then that will coincide with the Hodge numbers in Lund-Pijarkowski. But this is this number matches is coming from some non-trivial fact from analysis. All right, so finally I can explain the theorem that's sort of claimed in the title of the talk. So if you have a pair of the Petri surface and a smooth entangled divisor, and so we call it this pair is close to large complex structure limits if D is close to a nodal curve. And then we consider the TNL metric on this complement. And I would check the exact TNL metric on the complement, which is sort of like, you probably want to think of it as like you taking you view this as a symplectic manifold and you take the monotone symplectic structure. And on the other hand, and so for each rational surface or ID fiber, and this is Lagrangian pair, and so the Torelli theorem has a Torelli theorem by Gross-Hakenkiel. Inside its deformation family, there's a unique element inside this deformation family with trivial periods. And I would denote this by Y check E. So there's a distinguished complex structure, sort of like mirror to the monotone simplex structure under the Petri surface. And so what SYZ mirror symmetry would prove is that you can find a complex moduli of the pairs of the Petri surface with smooth entangled divisor. Technically, we need to have more decorations to the Kähler moduli of rational surface for this particular rational surface, such that the spatial Lagrangians that constructed on both sides, they're dual torus of fibration of each other. And so, so this sort of like I think this is probably the only example of like really the true spatial Lagrangian fibration due to each other. That in this sense. And mirrors are connected. So, so the mirrors actually they're connected by hypercure rotations, by two hypercure rotations, but these two hypercure rotations do not lie on same twisted line, and so it's slightly weird. When you do the hypercure rotation, they will match two of the hypercure triple, but not the other one. And so one can actually ask questions that can we tell what are the superpotentials for the Petri surface? And this is a work progress of my students, and so he was trying to prove that it's compatible with the superpotential. And so this will help to encode some information from, hopefully we'll be able to extract some information from Ricci flat metrics that there are some enumerated invariants inside. Right. So there's also some So I earlier asked like a similar questions, how do we extract the superpotential from the SYZ fibrations? And so this is a joint work with Shuchen Liao and Zhongzhu Li, that if you have a family of pairs, it goes to large complex structure limits. In other words, that this smooth angle divisor degenerate to a nodal curve. Then for each t not equal to 0, you can take the complement we call xt, and you do a hypercube rotation, you go x check t, and you can compactify x check t to rectangular surface. But there's no such rectangular surface corresponding to t equals 0. But the interesting thing is that the y check t will converge to a complex manifold. And this complex manifold actually is interesting in terms of mirror symmetry, and that is exactly the compactification of Landau-Ginzburg potential of y. And so recall that the y is, you view this as this monotone symplectic manifold, the complex structure here really doesn't matter. So this is like a auxiliary choice. We sort of construct the mirror in flow theory, and then we compute this limit by hand, and we prove that they're the same thing. And this generalized the mirror symmetry of P2 earlier, that I said that hypercube rotation, if the mirror, in the case of P2, this is in general not true, but you need to take limit towards certain large complex structure limits. And so that is the slogan. You take the large complex structure limit of hypercube rotation, you get a mirror. And so actually this helps us to compare the SYZ base with the fine structure that is being used in the work of Karl Pompola-Sieber. So I probably still have some time to talk about applications. And so are there any questions? Right, so so first from this two spatial Lagrangian fibrations, the first thing we found, actually, we discovered some new Ricci flat metrics. And so given a rational surface with an ID fiber, we actually found in one prime family of Ricci flat metrics with high metrics sort of like it happened this quickly, like index by Z. And how we discovered this via the SYZ fibration is as follows. If they're only high symmetric, so we start with a Depatto surface with a random smoothly curve. It's an anti-canonical divisor. And to get a complement, we produce a SYZ fibration. We do a hypercube rotation, compactified to rectangular surface with an ID fiber at infinity. There, if we get high symmetric, then we can produce, by the theorem, that you are going to produce another spatial Lagrangian fibrations. And then you hypercube rotation back to the Depatto surface. Then you get two spatial Lagrangian fibration with phase differ by pi/2, actually. But that will force the curve, the smooth angle divisor and the Depatto surface that I start with has rectangular fundamental domain, which is absurd because I can start with any smoothly curve to start with, and that gives you a contradiction. And so actually they give you, so the answer to the second motivation question that I mentioned earlier, the answer is actually no, there's actually more metric. And so actually we also even be able to write down a new sort of like a n sets that generalize the semi-flat metric of Green, Shapiro, Vafa, and Yao. And actually using this, we actually get more Ricci flat metric away from large complex structure limits. So if you recall that the theorem of High that he proved, he only solved this complex Monge-Ampère equation for this alpha is large. We also solve for when alpha is small, which is And so this alpha here is an interesting parameter. So in terms of mirror symmetry, you can view this as like when alpha is large, this is like a going to large volume limit. So the one first application is discovery of some receive flat metrics. And so this also gives a proof of Torley theorem for certain gravitational instantons. So gravitational instantons are the building blocks of Hawking's quantum gravity. And mathematically, they're defined as the non-compact hyperkähler surface was bounded out to curvature. And so it's classified by Sun and Zhang that all the gravitational instanton are in this types. So they have volume growth R4, R to the 4, this is full volume growth, and R cubed, R2, and R. And they behind he found another two type of gravitational instanton was the same volume growth of R squared as LG, but with a different curvature decay and this LH star. And what LH star is those like a non-compact Calabi surfaces was bounded out to curvature, which at infinity is modeled by the Calabi n sets. And so, so the SYZ vibration that we constructed used to prove the following Torley type theorem. So if you have two gravitational instantons, which is of type LH star, that means that infinity is modeled by the Calabi n sets. If there is some diffeomorphism such that it preserves the cohomology class of hyperkähler triple, then you can actually promote this diffeomorphism. You can modify a little bit such that it preserves not only the cohomology class of these two gravitational instanton, but you make identified the hyperkähler triple and the differential form level. And so this is an analog of the result of Perheimer for when people start to understand the gravitational instanton for the type LE, and this is the starting point. And so our results sort of like, although it's start from mirror symmetry, but it has quite some applications outside of mirror symmetry. And also there are some fun applications in maybe in algebraic geometry. There are some classical theorem. You start with the smooth curve in P2. It's well known that you can find an automorphism of P2 and which preserve the smooth elliptic curve. And there's always like Z3 plus Z3 inside the automorphism group of P2 that's fixed any cubic. And coefficient, you don't require any symmetry. And the special Lagrangian fibration will actually help to do this because that on the complement, you know, there exists a special Lagrangian fibration. You do a hyperkähler rotation, and then you compactify to right-wing surface. There, you can find a Z3 times Z3 that fixed the hyperkähler triple there by using the uniqueness theorem, and which is crucial in this case because receive flat metric is not unique, and so you really need some kind of uniqueness theorem to pinch this part. And then you can prove that once you find this Z3 times Z3, which acts on the right-wing surface, you can do a hyperkähler rotation back with a little bit more analysis. You can prove that actually it gives you an automorphism of P2 preserving the elliptic curve. And so I think this is a one-page proof in algebraic geometry, but we actually have 100 pages in terms of analysis, but we covered this very classical result. And so finally, I will mention that I know this workshop is about Lagrangian interiors, and so most of the talk is not directly related, but to echo with the thing of the conference, that there's an ongoing work whereas Tristan Collins that we're going to construct new spatial Lagrangians in some Lagrangian gap pairs. And so there will be more implications and mirror symmetry on the way. Maybe I should stop here. Thank you.
Yeah, I think there was a question by Gordon. Is that?
Sorry, I hit the wrong button.
Immediately received function. Okay, any questions from the room? Any questions from Zoom?
Actually, maybe I have a question.
Yep.
So at some point you have this parameter alpha, and you are able to produce metrics depending on alpha.
Yep.
So first I wanted to check, is alpha somehow related to the size of the Lagrangian torus fiber somehow?
Yes, exactly. So
probably when alpha is big, the size is small, probably. Is it the correct?
I think that it's the so this alpha, well, okay, so maybe where should I put it? So yes, so this alpha here. So recall that there's two sides. So there's the Petro surface side and rational surface side. On the Petro surface side, so this alpha is sort of mirror to the imaginary part of the modulus tau. And so when tau, imaginary tau that goes to infinity, then what's happening is that the SYZ fibration is collapsing inside the Petro surface side. And so that is the reason why we say that when D is degenerate to a nodal curve, we say that's a large complex structural limit because we see the SYZ fibration is collapsing. And so on the other hand, the SYZ fibration here, so when alpha is large, that actually shows, so the SYZ fibrations here has large volume because it's mirror to that.
Other questions? So I have a question. So at the end, so this again, like the final SYZ fibrations that you mentioned are like actual SYZ fibrations, right? Not this almost SYZ vibration.
Yes, exactly. This is a true spatial Lagrangian fibrations. Yeah.
Okay.
I have one question.
Okay.
Yeah. So like, what if you have a rational elliptic surface without a section? Let's say you blow up 9 points on a cubic, so that it's like the line bundle is like 2 portions on a cubic instead of trivial. So there's like some pencil, but with a multiple fiber. Is there some expectation that you'll have a hyperkiller metric on that too, or?
Yeah, that's a good question. I don't know at the moment, because probably depends on what you want. Because like say for example, you can always like do this logarithmic transformation on one of the fiber, right? And you remove it, but then the complement is actually not like as a complex manifold. It's actually not changed, right? So the original hyperkiller triple also always live on the complement without any changes. So in that sense, that in quite some examples, probably you mentioned probably also sort of cover in this sense.
Thanks.
Okay. There are no other questions. Let's thank you, Shen, again.
Thank you.